Hello, everyone. We will continue studying Task 2, Verifying Ohm's Law in this lesson. In the previous lesson, we verified Ohm's law through two experiments and established the following two principles. 1. When resistance is constant, current and voltage are directly proportional. 2. When voltage is constant, current and resistance are inversely proportional. This law, known as Ohm's law, was introduced by the German physicist George Simon Ohm in his paper, The Galvanic Circuit Investigated Mathematically, published in April 1826. As research into circuit operation progressed, the significance of Ohm's law became increasingly apparent, leading to a substantial enhancement of Ohm's reputation. To commemorate Ohm's contributions to electromagnetism, the physics community named this Ohm's law. Additionally, the unit of resistance was named the ohm and is represented by the symbol omega. Moving forward, we will delve into the following concepts to better understand Ohm's law. 2.4 Supporting knowledge and skills. 1. Voltage. As shown in the diagram, we often see a label on batteries and electrical devices. This label usually includes a number and the letter V, such as 3.7V, 5V, 220V, etc. This notation of number plus V represents voltage. For instance, 3.7V indicates a voltage of 3.7 volts in the diagram. Let's start by using a water analogy. We know that the position of a water tower is always higher than the outlet of a water pipe. Water flows through the pipe because of the pressure created by the difference in water levels between the high and low points. Now, consider this: if we were to raise the outlet of the water pipe above the height of the water tower, would water still flow out? Similarly, electricity works in a similar way. Current flows through a conductor due to the difference in electric potential energy between high and low potential points. This difference is known as potential difference or voltage. In an electrical circuit, the potential difference between any 2 points is referred to as their voltage. For example, in a 1.5 volts battery, the positive terminal is 1.5 volts higher than the negative terminal. Voltage is symbolized as U and is measured in volts, represented by the letter V. Voltage can also be expressed in microvolts, μV, millivolts, MV, and kilovolts, kV, with conversion relationships based on kilo unit. 1 kilovolts equals 1000 volts, 1 volt equals 1000 millivolts, 1 millivolts equals 1000 microvolts. 2. Current. Under the influence of the voltage provided by a power source, free electrons, or charges, within a conductor move systematically in response to electric field forces, creating a phenomenon known as current. Conventionally, the direction of positive charge movement is considered the direction of current flow. Current is symbolized as I and is measured in amperes, denoted by the letter A. Apart from amperes, commonly used units for current include milliamperes, mA, and microamperes, UA, with conversion relationships based on kilo unit. 1A equals 1000 mA, 1 mA equals 1000 UA. Now, let's ponder this. While the water level in a water tower may be high, without opening the valve, water won't flow through a channel, and a continuous flow won't form. Similarly, if there's no path for charges to move in an electrical circuit, a current won't emerge. Thus, for current to flow in a circuit, two conditions must be met. A. There must be voltage, or power source, in the circuit. B. There must be a complete path for the current, or a closed circuit. 3. Relationship between voltage and current. Consider this in your everyday experiences. When the size of a water pipe remains constant, how does the flow of water change as the height of the water tower increases? Right, the taller the water tower, the stronger the water flow. Conversely, with a lower water tower, the water flow is weaker. This difference is due to varying water pressure. Similarly, when water pressure is constant, a larger pipe leads to greater water flow, while a smaller pipe results in lesser flow. This phenomenon is attributed to the varying degrees of resistance the water pipe presents to the flow. In our previous lesson, when we conducted two experiments to verify Ohm's law, the relationship between electric current and water flow became quite analogous. The size of the water pipe is analogous to the magnitude of the resistance. The amount of water flowing corresponds to the electric current. The height of the water tower mirrors water pressure, which is analogous to voltage. In essence, the relationship between voltage and current is similar to that between water pressure and water flow. When resistance is constant, higher voltage leads to a larger current. When voltage is constant, higher resistance results in a smaller current. We have now completed the explanation of the content regarding Task 2, Verifying Ohm's Law. Let's now take a moment to review the key points covered in this section. A. To learn the method of controlling variables to investigate the relationship between current, voltage, and resistance. B. Develop a deeper understanding of voltage, current, and resistance through analogies. C. Acquire the skill of applying Ohm's law. The current through a conductor is directly proportional to the voltage across it and inversely proportional to its resistance. I equals U divided by R. Ohm's law is a fundamental principle in electronics and can be used to solve various problems. That concludes this lesson. Thank you, everyone.